Thank you for downloading and installing Adapt Builder 2018. This demo is intended to provide steps to build a two-way slab with post-tensioning and run through the modeling, analysis, and some design checks for the two-way slab. If you have questions as you're working through the demo, please feel free to contact support@adaptsoft.com. We're going to go ahead and get started, and we have a multi-span structure that we're going to work on. Let's go ahead and open the application. On your end, if you'll go ahead and just launch Builder after installing it, you should receive this splash screen shown here, Builder 2018. And if you select this arrow down, this allows you to select the modules that will be in use. So today we're really going to be focusing on a single floor with post-tensioning. So we want to have Floor Pro turned on. This allows us to design and analyze a single floor. Edge allows us to analyze a multi-level structure. So we'll have that turned on also. And then if we go to the mode, we can either do an RC structure or a hybrid structure with or without post-tensioning. We want to make sure we select PT and RC. For the modules, we'll leave those blank and select your proper unit systems or unit system that you'll be working in. Today I'll be working in US units. You can follow along and just employ other unit systems, SI or MKS, if you're using that particular unit system. We'll go ahead and select OK, and the interface will open. As we work through this example today, we'll talk about some of the ribbons and some of the tools we're going to be using to build the model. One thing I'll point out is that today we're going to be using just the native tools in the program to construct the model. If you have a CAD file or a Revit model, for example, we have options to import those types of files into Adapt for the construction of a model, and that is a bit easier to do and less time consuming. So if you use that method, you can always select File, Import, IMP or DWG. IMP would be used for a Revit file. DWG would be used for a CAD file. And we have additional videos at youtube.com/adaptsupport that show the process for importing those types of structures. My recommendation would be to follow along using native tools, build the same model that we're going to build today, and this should help you move along and get familiarized with the interface and with the process needed to generate a model and process a model. So the first thing we'll do is we'll go ahead and save this model. When you're saving a file, make sure you don't add any special characters. If you need to use a separator, use the underscore separator or just run the characters together. I'll save that locally to my machine here. You'll want to do the same on your end. I would not advise saving it to a network location. That may result in some permissions that may cause issues with running the file. So the next thing we're going to do is just set up some of our criteria. I'll go here to criteria. Under design code, we'll select the design code first. We're going to use ACI 2014. I'll go ahead and select OK. For the analysis and design options, we'll talk a little bit more about these. We want to make sure for single level we have the proper support conditions that the program will auto create when we analyze. And we're going to say that the base of the columns and walls will be roller supported and rotationally fixed. This essentially mimics the ability to allow for free shortening in the plane of the slab, and also to mimic a multi-story slab, for example, that may be at level X in a structure and have the ability to translate laterally. So as a user, you can modify this to fix fixed or select user settings here. If we go down to the rest of the options, we're going to leave these as defaulted to for now. If there's a need to come back to this, we will. We'll select OK. Because this will be a post-tension slab, we want to make sure we set our allowable stresses relative to the code, and these are all already defaulted to relative to ACI. So for two-way slab criteria, we're using 6 square root of F prime C for our allowable stresses for sustained and total stress. And then our initial stresses are shown here as a function of the F prime CI. We'll talk about that in a moment when we go to criteria. For shear design, two-way shear design, punching shear, essentially we're going to use 1/2 inch diameter studs for the reinforcement. We'll assume that the program, or allow the program, to generate the proper number of rails per side. So I want to limit the rail spacing, and I want to provide uniformity and uniform spacing of the studs. Tendon heights, the default tendon height we're going to use is 1 inch and 1 inch from top and bottom. So if we have the CG, let's say at a support from top to CG of the tendon at a support, we'll say it's 1 inch, and the same from bottom fiber to the sagging tendon at the centroid, let's say at midspan and positive bending moment region. This can be modified again by the user. As per this demo, we'll just use the 1 inch. For cover, we're also going to use 1 inch. This is just rebar cover. This is the calculated rebar that the program will produce when we go and analyze the design strips. Notice this is two-way, one-way, and beam. In this example, we're going to be primarily using two-way criteria. If you do have beams or one-way slabs in a model, then you could use additional inputs for those types of design criteria. The size of rebar we're going to specify for the two-way slab will be number 5 bars, top and bottom. These are the preferred sizes that we want for the longitudinal flexural reinforcement. And rebar roundup and spacing. This just allows the program to apply some roundup values for length. So the program will round up to 6 inches. Spacing will be rounded down to 1 inch. Stirrup spacing, this doesn't apply for this example. And then rebar lengths, we want to make sure that the bars that the program calculates for minimum requirements, for example, extend either side of a support by this value as a function of the span length. This is at the bottom of the slab, so from midspan, left and right of midspan, it's 1/3 times the span length. And then we can also input an extension for the reinforcement beyond point of zero moment. So we'll leave these as the defaults. We'll leave all of these turned off for bar length adjustment. We'll now go over to the material properties. For concrete, we're going to assume that the concrete strength will be 5,000 for walls, columns, and slab. If we wanted to, we could add additional material properties and write naming here. So we might have one called 6,000 psi, for example. And then we would want to change this, just change the different characteristics of that particular property in the input screen here. For reinforcement, we have one material here of mild steel 1. We'll change the modulus here to 29,000, and that's the only change we'll make there. For pre-stressing steel, I'll change this modulus here to 28,500. These are actually conversions from base metric that we're using, so we want to make sure we convert to the proper US unit equivalent that we want to use for defining the material property. Steel fiber and generic don't apply to this model. The next thing I'll do is just go up to model, and I'm going to set up my levels in the model. So again, we're only really designing one level in particular, but we could, at the end of the demo, we're going to show how do we copy that level vertically to additional levels if we wanted to then expand the model into a multi-story model. So bottom plane, we're going to say, we're just going to call this ground level. I'm going to call this level 2 is the level we're actually going to design. We'll call this level 3. We'll leave the story heights to 10 feet. And then I'm actually going to add 12-foot stories. I'll add 3 of those and rename the levels. This will be level 4. This will be level 5. Make sure I apply that. And level 6. Okay, so make sure you have the levels set up here in the reference plane manager. Looks like the story heights need to be updated. Let me go ahead and change that there. I'll say apply. And we'll say this is also 12 feet. Now, we haven't added anything yet to the model. We just want to confirm the levels. So right now we're looking at a top view. You'll notice there's some quick access buttons, mainly snap tools, grid settings, and then we also have this option for different view cubes, top view, front view, isometric or three-dimensional view, extents, and so on. Those are also located in the home menu under the zoom camera panel. So we could go here. For example, if I wanted to go to a front view, I could use this static tool here. This obviously is static, but if you change the ribbon, it goes away. So either one will work. We'll go ahead and I'll just look at an elevation view. And you're going to notice, let me go to this view here. You're going to notice the program only shows ground floor, level 2, and level 3. So it's important to understand the state or the mode of the program that you're actually working in. And right now we're working, I'm going to go ahead and circle this for you so you understand where we're at here. This is the mode you're in. So this is called single level and this is called multi-level. Not only do those change what you're graphically seeing on screen, they also change how the program recognizes and auto-constrains the supports when you actually analyze the structure. So we're mainly going to be working in single level mode, meaning if you had a 20-story structure and you only want to focus on designing level 10 in the same instance of the program, you can just switch to single level and actually analyze only level 10, for example. And in this case, we're talking about level 2. So right now we're actually in single level mode and the active plane is shown as highlighted red here. That's level 2. So anything I model will be modeled at level 2. If I add columns or walls, those will be referenced from level 2 downward to level ground or ground floor. And I can navigate, I can switch this. Now I'm working at level 3. If I switch again, I'm working at level 4. And it will always show the level above and below immediate levels from the active plane when you're in single level mode. If I go and switch over to multi-level mode, you can see all of the planes. The active modeling plane is still 4, but now I'm seeing everything in view. So this is again an elevation view. If I go to a top view, that makes it a little bit different, difficult. I know that I'm actually active in level 4, but I'm in multi-story mode. So anything I model is relevant always to the active plane. So we're going to switch over to single level mode, and notice if you hover over a tool, there's a description. If you want more description, for example, you can pull this arrow down and this will give a little bit of a more guidance as to what the tools are. You can also access documentation from this location here under the help menu. Okay, let's go ahead and start modeling. So we're going to switch our active plane to level 2 and we'll go over to model. We're going to primarily be in modeling. Don't let these buttons fool you. These are to add or model a component. These ones here are to turn off and on the visible display of a component. So if you select this and nothing happens, you're probably just turning the component off and on. We're going to start by we're going to go ahead and just start by modeling a column, and then from that column, that will basically be our origin and reference point. We can move it to another origin location. We're just going to arbitrarily set the location. So I'm going to go ahead and select column, and when I add the column, the program is going to use a default size. It's 12 by 12 inches. If I go to item properties, I can switch the properties of the column. So this first column is going to be 20 by 20. We're setting it to material 1. Everything will be set to material 1, and it's defaulted to group 1. We won't manage our components in groups. There's other ways to filter the visibility of components that we may touch on here. So we'll just select the green checkbox. That changes the size, and I'm just going to go ahead and place the column at this location. Now from this location, I have additional columns and walls that I need to place. So we're going to take this column and I'm going to select it. On your end, you're going to want to follow along, select the column. We're going to select modify, and I'm going to copy the column downward. So we're going to copy it 30 feet in the negative y direction. It's going to be negative 30, and we're looking at this global axis and positive convention. I'll copy that column. And I want to copy it again 30 feet. Now I could have just taken this and copied it twice 30 feet, but we're going to take it step by step here, and we'll go back, select this column or this column. This will be copied 60, this would be copied 30. I'll use the same tool. It's under modify by coordinates, and this will be again negative 30 feet. We'll say copy that column. Okay, we have our 3 columns in line on this side. This column is going to actually get moved over another, let's say, 28 feet. Okay, so we're going to go ahead and say this is in the positive X direction, 28 feet. And then we have a wall. And that wall is actually going to straddle this. If this is a grid, we're kind of working without grids here. We could add grids, but we're going to build the model gridless in this case. And if we go ahead and select this line, the wall is actually going to be 5 feet on this side, 5 feet on this side. So we need some way to reference the wall, and it's actually in line with this column here on the same grid. So how do we do this? We're going to go ahead, and I'm going to just use construction lines. So I'll make sure I turn on my snap tools. Snap tools can be found in the home menu or down at the bottom again. And I'll turn on snap to endpoint and turn on orthogonal mode. And that allows me to create some nice construction lines here. So once I do that, I'm just going to take this and I'm going to copy that line, and I'll copy it over 5 feet. And then I'll copy it again and just go back to the same command, and we'll copy it negative 5 feet to the other direction. Okay, and I know that the vertical leg, this wall actually looks something like this. The vertical leg is 5 feet. So I'll take this line again, it's already selected, and we'll copy it negative 5 feet. So in the absence of any grids, or a grid file, any imported CAD file, this is really how we're natively modeling in the program. And this hopefully will help you get kind of accustomed to some of the tools necessary in modeling and using the software. Again, using CAD files and Revit imports is obviously much easier, but this should help you get your feet wet on using the software. So we'll go back to model. I'm going to model a wall. The wall thickness we're going to say is 12 inches. And we're going to go from this location, this intersection here. I'll turn on snap to intersection. I want to turn off snap to orthogonal. Now you can see it's you can rotate rather than be aligned X or Y. And this becomes our wall for this location. Okay, now I want to copy that wall, and I actually want to move this point to an intersecting line along this column. So I'll just take this. I'm actually going to press Control C and Control V to copy. And I'll take this and this, and again, instead of Control V, Control C, I want to copy with a base point. So we'll go ahead and I'll use modify in plane. We're going to say I want to copy this point down to there. Okay, and now I want to rotate this object here. Let me save the model. We're going to rotate. The center of rotation will be this line, and we're going to rotate this by 180 degrees. And that's the other wall stack that we have. Okay, from this location at this column we have a step in the slab. So this next column that we're going to model is actually right here, and then we have a bit of a jog in the slab here. Looks something like that. So this jog is going to be 2 feet. So if I basically just take this column and I copy it down by coordinates, I'm going to go in the Y direction -2, in the X direction it's another 28 feet. We'll say copy, and that places that column. And we'll go ahead and we'll just copy that one over 30 feet. I'll go back and change the sizes for the columns. We'll do that once we actually place them. So we'll use the move by coordinates again, or copy by coordinates. This again is 30. And now we have mainly our columns positioned. Now here, if we take these two columns, I want to copy those down by 30 feet. So this will be in the negative y direction. Okay, and actually that's going to be 28 feet. We want to move those up by 2 feet. So let's go, this is going to be 2, and we'll just move those. And then we want to copy these again twice. So this is going to be copied down 30 and 32. So we'll go negative 30. And then we'll just keep those selected and say this is negative 62. And this is the set of columns that we're going to be working with. We have another wall that's actually located down in this corner. So I'll come back, create another construction line. I want to turn on orthogonal mode, so we'll just run that out to there. And I'm going to copy this by a reference point using keyboard. So if you select the wall, press Control-Shift-C, we can create the reference point, which is going to be the bottom corner of the wall, and then we're going to move it down to that intersection point. Make sure you have Snap to Intersection turned on. Okay, and this is essentially the arrangement of the supports. Now let's go ahead and everything here is a 20 by 20. We do have some different columns. This column, for example, will be a 20 by 30. So the A direction will be 30 inches, the B direction 20. We're not rotating the columns, so we're using this convention here. The R local axis is in conjunction with the global X axis, for example. This one will be 20 by 30, so it's rotated. Okay. This one also will be 20 by 30. So if you double click on any component, the properties of the component will open. Actually, I'm sorry, this is 22 square, as is this one. Okay, these two are also 22. Now if you want to change multiple components at the same time, you can select them. You always want to use modify selection under the modify ribbon. So here we're going to go to column, and we're going to change that to a 22 by 22. It's already set. And last couple of columns, we have a 30 by 20 in this location. And the same thing here, we have a 30 by 20. I could have selected both of these again and used modify selection if needed. By default, all of the columns are fixed to the slab. There are no releases by default. We would have to set up a release as a property of a column in the properties here. You can see for translation and rotational fixity, everything here is fixed. A checkbox would mean that it's released, or a check mark. I'm now going to add a couple of openings before we actually enter the slab. So let's save the model. I'll create another construction line in the orthogonal mode. We're using that mainly to generate the opening. We'll go back to model. Remember, this is kind of your anchor for anything you're modeling in terms of components. And I'm going to just create an opening. Now, openings can be a little difficult to create in orthogonal mode, so I'll come out of that by using or disabling the snap orthogonal. I want to have snap intersection turned on, and you can see we have a couple of openings that we're going to create at these wall locations. In terms of the slab, and the slab, let me go ahead and mark this. This is going to be, we're going to have a step here. This is like a 2-inch step down to the face of this column. And then we have a step here. This will be inward by 4 feet. It'll be at the face of the column. This will just be at face, and then this is going to run out to, actually this will run out to here. Let me go back up for a moment there. So at this location, at that end of that wall, this will come down 4 feet, and then at midspan it'll come back up something like that. This is the slab outline, edge of slab. It's a little bit sloppy there, but we're going to see if we can go ahead and create that. Now before we create it, again, we don't have a polygon that we can convert. I'm going to go ahead and just delete these lines. I'll select and delete them. And we're going to create some construction lines so that we can get this slab aligned. I'll go back to Home, turn on the Line tool, and I want to snap on the corner of that column. But in order to do that, I need to turn on this option that says Snap to Vertices of Components. And if I do that, then I'm able to snap to different corners of objects. I'll go into orthogonal mode, and you'll just see I'll start creating some lines here that allow me to align the slab edge. Now here, this kind of intersects the outside of that column, so I'll come back and I'll actually align it with the outside face of this column. I'll just draw this line all the way down. Let me do that again. I'm just using the most outer bound face of any column as my edge of slab. Here we're going to do something like this. This is where we have that 4-foot step inward. Now in order to create that, I'll take this line and I'll go back to modify by coordinates, and I'm just going to create a new line inboard by 4 feet. We'll say copy. We'll come back to Home and again use the Line tool to generate some construction lines. These will all be erased at some point, but they're nice to use while we're trying to model the slab here. So I want to go ahead and create a line from, I'll turn off orthogonal. We'll create a line from center to center of column, and then I'm also going to create a line that marks the midpoint. So to select the midpoint of that line segment, I'll turn on the midpoint snap. And notice it's askew, so let me delete that and go back to orthogonal. And I'll need to open the command again. Just create something like that. And we need to then offset this by 4 feet. This will be offset -4 feet. We'll say copy. This is going to be offset by -4 feet in the Y direction. We'll come back to Home and again open the Line tool, and I'll make these intersect. There's the bump out, a little balcony there, and then the balcony will actually step back to this location here. And this is just a rough outline of our slab edge. So now if I go to model, I'll turn off orthogonal again. We don't want that on. I'm also going to turn off snap to intersection and snap to midpoint. I really just, let me turn back on snap to intersection, turn off snap to vertices of components, because you'll have too much of the program will click on different points that you don't want to accidentally snap to. So we'll go to slab, and now it's asking me to start drawing the slab. Now I could go in and just enter coordinates. I'll close that and I'll just graphically model this. If you make a mistake, I made a few mistakes there, just use backspace to undo, and that's a nice way to go back to where you were. You don't, or you could close it, just continue, and then come back and delete the vertices. So let's go through and draw this slab edge. I'm just snapping on the intersection of these construction lines, or grids if you import a grid file. This needs to back up. I'll press backspace. This is our balcony that steps out. And here you can see we actually made a mistake. This line here should project down. That's okay. We'll just go ahead and press enter to close. That closes the polygon draw, and then we'll escape out of the command. Now I want to move this point of this slab over. Notice when I select that, it actually selects a line. The line and the slab region are in the same space. So if you press tab, it will toggle between the two. Or I could delete the line out and get rid of it so I don't have to toggle. So here if I toggle, I want to move this over, but I need a construction line. I'll come back to line and I'll go from this point down to this line. If I use snap to perpendicular versus orthogonal, then I can get a nice aligned edge there. And I'll exit out. I right click exit out of the line command, and we'll move this over to that point. Okay, now we have our slab edge. Now I want to delete these lines. They're a little bit sloppy. I don't want to accidentally select them and have to work around them. I could turn them off, or I could delete them. To turn them off, I can go to the layer settings from the home menu, and if I just alphabetize this, we're going to go all the way down here to adapt line, turn that layer off, and they're gone. Or you could, let me turn the layer back on. Another option would be to delete them. I don't want to have to manually select them like I'm doing now, pressing Control on the keyboard, so I can just select by type from the home menu for any component, line, and delete. Okay. All right, the last thing we're going to do, we have a couple of slab thickenings in this model. So this model, we're going to double click on the slab. It's 5,000 psi. It should be assigned to concrete 1. We'll say it's a 7-inch slab, but we have an area that we want to use an 8.5-inch slab. We're going to have some heavier loading here, and also a depressed slab for balcony. The depressed slab is going to be over in this location, and the thickening will be here. So this is going to be 8.5 inches. And then we're going to have basically a step here and here. This will be step. This will still be 7 inches, but we're going to drop it down by one inch. So how do we do this? We can either use adjoining slabs, or we can nest slabs. And there are pitfalls, I think, to either method. For a single level slab like this, I'm just going to nest the slabs on top of one another. So I'll go ahead and I'll just create, again, a few construction lines. I'm going to take this point, and again I'll use orthogonal, and this point an orthogonal, and I want my slab to essentially be modeled somewhere here. This is not perfectly aligned, but that's okay. We'll just model the slab into that point. That there's still an opening there, so we'll do that. And then here I'll go from there, something like that. We'll go back to model, and I'm going to create a slab, and we want to turn off snap orthogonal. Now we could actually work around this. I mean, I could model, from this face down and create a few steps, but that's going to create densification in the mesh, having little tiny edges of slabs exposed like that. So the name of the game here is to keep things aligned, and we'll keep this aligned like so. Probably the safest thing to do is really adjoin slabs. So once I actually do this, then I can modify this slab region. For example, I'll move these points around. Before we do that, we'll go ahead and notice I'm selecting that line. If I press tab, I toggle to this slab, but I want to open the properties. So I can open the properties from the model tab, I can open it from modify tab, or I can open it from the active or the user bar down below. And we'll use this option here, item properties. This will be an 8.5-inch slab. There will be no vertical offset. This is 0. So that's in the same plane top-wise as this main slab. It's just thicker. We'll go back to model, and we're going to now create this slab. Okay, this one will have an offset. So again, I press tab to toggle, use item properties now from the modeling menu in this case. This will be 7 inches, but we're going to offset it by one inch. A positive value is downward. I'll go ahead and select my lines, going back to home, select by type, select lines, and we're going to delete those lines. Now I want to readjust this slab. I want all of my slabs adjoining. Again, that's probably the safest way to model slabs without causing any unforeseen issues with mainly with column design and some other areas of the program in terms of visibility. So I can take these points and move them. Here I'll just move this up like so. We have some redundant points. I can always right click and delete, or I can go back to modify and remove a point. So here we'll remove point 1 and 2. Let me save that. On the other side, again, we have this first slab that we entered. I'm actually going to remove, I'll move this point to there, and then I can flip this point over and move it to there, and I'm done. That modifies the slab. If we wanted to review some of the geometry, we're going to go over here to visibility using a section cut tool. I'll select point 1 of the cut, point 2, and the insertion point, and we can see that there's a little notch there in the slab. And the same thing here. Here's our 7-inch and our 8.5-inch slab. Okay, we could take that through frame lines as well, and it will show the columns and walls. It's a nice tool to verify geometry. We can just select those and delete them. Okay, the next thing to do in terms of the component modeling is to generate offsets for columns. For example, if I use the section cut tool and I look at this column, that column is protruding above the slab. So we want to make sure that that's offset. One way to do this that applies mainly to single level slabs is to use model connect supports. This will just offset the supports vertically. In some cases, that tool is not as useful, especially when you have very complex geometry and you have supports that might be touching two different slab regions that have different thicknesses and different offsets. So you may want to manually modify offsets, making sure that the slab or the wall is within the body of the slab, or the column or the wall is in the body of the slab that it's actually touching. In this case, it's safe to use that tool for this particular slab. Now the next thing we're going to do is add loading. So we're going to switch over here to loading, and we will go to load cases. We're going to primarily use the reserved load cases in the program. The gravity loads will always be defined mainly under general loads. We have dead load. This is really superimposed dead load. This is unreduced live load. We're not going to reduce the live load for this example. Live load reduction can be done for horizontal elements using subregions or skip patterns over here. We do have additional videos that touch on that. This particular reducible tag here is really only for vertical components like columns, and it specifically applies to design of columns with reduced live loads. So for this example, we're just going to set the loads as dead or live. You could add additional loads here, gravity loads, just selecting add and then relabeling it and creating your own load cases. This block down below, building loads, this only applies to loading a multi-level structure. These load cases are solved for only when you run a multi-level model, so this doesn't really apply to this model. Let's go ahead and load this. If we select our slab regions to load, the way this will be loaded, this will be 20 and 40. This is dead live for both this region and this region. This one here is actually going to be 20 and 100. You need a little thicker of a slab here, or more PT. In this case, we may have both. So we'll select the region. Another purpose of creating adjoining slabs is you can map slabs to the selected regions without creating more load in a region that you want. The program always accumulates load. It's cumulative, so if you have loading that overlaps, it's again additive. You can enter negative or positive loading in any direction, X, Y, or Z. In this case, because we've selected the load or the slab regions, we're going to select patch load wizard. Patch load, also known as a uniform load. For dead load, we'll say that this is 0.02 KSF. I'll come right back to this. It's still selected, the slab regions, and make sure you enter for live load 40 KSF. I'll select the slab region below. This one I could have also selected for dead load, but we'll do this separately. This is again 20, and then the live load will be 100. Okay, if we rotate this, we'll go to Home and use one of these 3D views. We can see the loads on the structure. If you double click on a load, you can see the magnitude, the load case it's assigned to. Every load is unique. They have their own load case. Only one load case can be assigned to an actual load that's applied with magnitude. If it's not in the Z direction, we can go to loads and apply this in the X or the Y directions also. Going back to loading, you can show all loads. This just displays everything that you've added to the model. You can show only point loads. There's no point loads. There are no line loads. There's only patch loads. This turns on all patch loads, all line point loads. Or you can filter it further. So for patch loads, I might just want to look at the dead load. And that would show up like so. Now if you want to see the magnitude of the load, under the view settings, we could turn on the dimension, and that will actually show me the tag for the actual magnitude of each load region. Other ways to display load might be the reporting mechanism. So if we go to reports, graphical, let's say live load plan, this is just a title. This is mainly used for printing the load on the structure. This goes automatically to a plan view and shows you the hatched region of the load. Okay, I'll turn those off. And we're going to now review the load combinations. Now for this example, we're primarily looking only at the gravity design for post-tensioning, meeting serviceability requirements, and we'll show an example of evaluating the slab for ultimate level forces, for example, strength dead and live and strength dead load only. The program preloads this with just a few combinations for evaluating those gravity conditions. The user can add additional combinations. There's analysis and design option tags that are carried with the load combo. So for a service tag, the program would report stresses if it's post-tensioned. In other words, along the strips that we're going to develop, you're going to be able to review the top and bottom flexural stress, the pre-compression, the balance loading, and so on. It will also solve for minimum reinforcement because of these service tags. For these combination service, we calculate the minimum rebar. For combination strength, we calculate the rebar necessary to meet the demand at ultimate level. For initial, we check stresses at initial condition. We talked earlier about the initial allowable stress. And if needed, rebar could be added potentially because you have an initial overstress, which is allowed by some codes. If you wanted to check the model for crack deflection, then we have to add additional combos. So we're going to add a crack deflection combo here. I'll just add that, and we'll call this sustained CR. So we want to check cracking under the sustained load condition. I'll assume that 30% of the live load is sustained. And I'm also going to check cracking under the total load condition. This is total service load. So I'll say that this is 1 times all of my load components. Self, dead, live. The program auto calculates for self. So go ahead and make sure you add these two combinations. And then we're going to use this other tag called long term. This is really just a way to combine results of other combinations. So if I select this and I add one, I'm going to call this live load increment. And we're going to say that live load increment will equal total minus sustained. So we're extracting that differential between the two. And let's go back. I'm going to stretch this window out. You may want to do the same on your end. So I'll highlight this, and this is going to be 1 times total cracked minus 1 times sustained cracked. And then my total long-term deflection will also be tagged as long-term. Again, I want to combine the results. And we're going to say total long term was going to equal this creep factor. In this case, we just have to apply a factor of 2, for example. It might be something less depending on whether you have compression rebar, whether you're predicting it at some day in sequence other than, let's say, in service condition, maybe 5 years or beyond. So for total long-term deflection, we'll say this is 3 times the sustained cracked plus 1 times the live load increment. This is 2 plus 1, creep factor plus 1. So we have to account for the instantaneous sustained deflection plus the creep plus the live load increment that would come and go on the structure. This is, again, just an example. So go ahead and set up these combos. If you wanted to look at results of a particular load case or set of cases, you could always set additional combinations to no code check. That just means the program would not design for them, and you basically just get an analysis result. We'll select OK and go ahead and save the model. The next step will be to generate design strips. So in order to evaluate the slab and to produce reinforcement for the slab, we need to break this up into X and Y strips. So we might have a strip, for example, here. We might have another strip along this path, and these are just tributary regions where we might have strips, and along here. So mainly frame lines. If you were using the equivalent frame method, you might break this into different frames, and the strips is, I guess, analogous to that type of a breakout for frame lines. So we have X, and then we do the same thing in Y. In order to do this, we're going to use the floor design ribbon, and we're going to create what we call Xdirection support lines. And so X will be first, then we'll use Y, and I'll go ahead and I'll create my Xdirection support lines. I'll just start the modeling outside slightly out of the slab. We want to try to close off all of the support lines at the slab edge. It's not necessary. If we don't do this, then we end up having to use a component which is called a splitter. Splitters will largely be non-required once we move over to version 2019. But for version 18, this is the method that you'll need to use. So once you've created a support line, we've snapped on each support, created nodes along the support line. Once you're done with this, you can right-click and close that line. That keeps us in the command, but it just closes out that one instance or that line. We're going to, again, snap outside, click on support, end of wall, support, support. And here I want to turn on snap perpendicular, and we'll zoom in and make sure we snap on the slab edge. Again, I'll press enter to close that. You could right-click close, or you could press enter. Okay, and then the next line will be, again, column to wall endpoint, and over here we'll do the same. We have wall. Here the wall's oriented differently, so we'll just snap on the center of that wall and then enter. Now if you wanted to move a point, I can post move a point. I could take this and move it down, and then these points I'm actually going to just close them back off at the slab edge. Again, the functionality here has been improved for version 2019, which should be released September of 2019. So we'll come back and clean those up. We now have our support lines. We don't need any splitters in this case for creating proper tributaries. In fact, we'll go ahead and just test this. Use the option here for section design to generate sections new. This will actually create strips. You can see this creates a design strip. Here's 1, 2, 3, and 4. And then if we wanted to see the outline of the tributary, we can use this strip results visibility from the floor design. I can turn on, for example, the Xdirection strips. You can see this a little more clearly if you go to reports, and from the design strips report, click on support lines X. This will actually show the different views hatched. Here it is, design strips X. So something like that is a little more clean in terms of the view. Okay, these are the Xdirection strips. The Xdirection will be our uniform tendon direction. Just keep that in mind. Okay, and if you want to turn those off, you can just use this toggle off and on. This turns on the X, this turns on the Y. We haven't added Y yet. You can turn off and on the design cuts. So each one of these cuts that you see perpendicular to the actual support line is a design section. That's basically a data point where we're calculating actions for stress calculations and also reinforcement calculations. So the program is predicated on the availability of these in order to design the slab. And one thing we have going on here is we actually have section cuts extending through an opening. So you can see there's an opening right there, and this cut starts here and it goes all the way through it and over to the other side. This is not recommended. In order to break this off, we really want to modify this and basically have this strip get cut around this opening, because otherwise you get this program, the program will integrate over this path and you get an integrated set of design actions through a discontinuity. So to avoid that, we'll go ahead and I'm just going to delete out the design strips, and we're going to add splitters. We want to somehow bound off the openings from being cut through. So first thing I'll do is just create another support line. I'm actually going to create a support line from this point over to here. And this will just allow us to have some result in between two openings where we have uniform tendons passing through those. This is one way to actually eliminate the problem of having a design cut extend all the way through an opening, because now what will happen is this cut, it actually might come here and this cut might come up to here. In this case, this is still going to come through. So we need to use some splitters here. We're going to create X direction splitters. Select this option for X direction splitter. And we're going to start at the point that is inside of the slab region. I'm going to just click on the point of this opening just for alignment purposes, and then I'll click at this support line here and I'll press enter to close that. I'll do the same thing downwards. So select the same point using snap to endpoint and press enter when you've finished with that, and then we'll do the same thing on the opposite side. We actually missnapped. You can backspace again to undo. Now here you'll notice I messed up. I need to go back and just realign that. And we'll create another splitter horizontally. These are all X direction splitters because they are used to properly generate strips in the X direction. So once you've entered these splitters, and I'll label these, this is splitter 1, 2, that's from end to end here, and then splitter 3 and splitter 4. Okay. Once we've done that, the program can use those as virtual boundaries to create the proper tributaries. So if I regenerate the tributary, what you have now is this gets cut at that splitter. You see it extends into the opening, but there's no consequence to that, but it doesn't extend out of the opening. Same thing happens on this side. This extends to the face of the opening, but not out of the opening. And then we have this strip that's used in between the openings to give us some results there. Okay, so we'll go ahead now and let's turn off the display of the X direction. We'll just go up here to the strip results visibility panel and hide those. I'm also going to hide the splitters. I don't want those turned on. And we'll do the same process for the Y direction. So we'll select Y, modeling, and we're going to start bottom up. I would go left to right for X, bottom up for Y, just to keep the same convention. And we're going to snap at each endpoint of the walls. This will be the banded tendon direction. In this case, we're going to actually run a banded tendon along this path here. So I want to create another support line along that path. I'm kind of creating the lines where I'm going to add my banded cables. Notice I actually stopped at this point. I didn't extend it vertically like the one on the right over here. The reason is you cannot have intersecting support lines in the same direction. These are both Y direction support lines. They cannot intersect. So one stops at that point, the other one extends on. Again, snapping to each support, closing it at the slab edge. We're just selecting Enter to close. Here we're actually going to have two unique support lines like so. We could add another support line here. Okay, something like that. They don't have to be continuous. We're just creating data points in the slab with these support lines. Again, the main point is we want to have them where we have the banded tendons. Now I'll go through again just quickly and trim these off. These don't need to be trimmed off, but if you want a cleaner model, then you can always come back and post edit these. I like to just snap outside of the slab because it's easier to start the process of modeling the line when you don't have to zoom in and pick a point and adjust the snap tools. So in this direction we have three locations where we need splitters. We have a point here that terminates from this support line. That's inside the slab, this point and this point. So we're going to add a splitter from this point over to this edge of slab, over to this support line, edge of slab, and along here. This cleanly identifies zones. Here's zone 1, here's zone 2, and zone 3 where the program can break the tributaries up. So I'll use now my Y direction splitter. Go ahead and select Y splitter. And we'll start here. You want to have snap to endpoint turned on and press enter to close. They can either terminate at a slab corner or slab edge or at a continuous adjacent support line. Okay, and we'll generate the strips again. Now we have X and Y strips. If I turn off X, I'm left with Y, and we have strip 1, strip 1, strip 2, 3, 4, and 5, 6, and 7. In the X direction, we have what we were left with earlier. I'll turn off the splitters, and now we're ready to add post-tensioning to the model. In this case, we're going to use the mapping tool for the banded tendons. So let's turn on the the Y direction strips. I'm going to select each of these strips. Okay, and we're going to use the area of each design cut for the program to give us some guidance, let's say, or a starting point for tendon modeling. If we go up to tendon, we can either manually add tendons and change their properties, or we can map tendons. We're going to add tendons manually using the uniform direction. Here we're going to map banded. And we're going to use the design strip width, select that option. The force and profile optimization, we'll say that the average pre-compression we want to target for the banded direction, let's say it's 150 to 300. And the percent of the self-weight to balance we're going to say is 50 to 90%. This is for the load balancing. The placement of the tendons, we can either have the program create one group of strands. We're going to use 1/2 inch diameter unbonded cables. So if the need for meeting the pre-compression is 10 cables, then the program can say use 2 groups of 5 using this default option. Maybe we separate it by 1 foot. We might just want to idealize it as one group, where I would not model the tendons right on the top of the support line. It becomes hard to see them and hard to select. So maybe we offset them by 1 foot. This will be one group of 10, or we model all of them. This would be 10 1/2 inch diameter tendons modeled at this spacing. We're going to use 2 groups. So we'll offset this by 1 foot. The assumed effective force of the cable will be 26.7 kips. So if we take an effective stress of 175 as a pretty good target assumed value, multiply that by the area of a 1/2 inch diameter cable, 0.153 square inches, we get 26.7. This is equivalent to 118 kilonewtons metric. And then the shape of the cable is going to be identified here. The first span, mid-span, this should be plural mid-spans. We might have more than one mid-span, and the last span. Now you'll notice in our modeling of the support lines, we actually created these tiny little spans from center to edge of slab. That's going to come back a little bit to haunt us, but we'll use some tools to clean that up quickly. These are the inflection points. So x1 is a function of the span length. This is to the first inflection point, to the bottom point, and to the opposite inflection point. We'll say OK, and the program models the tendons. Okay, there's a few issues we need to clean up in this case. So the first thing is you'll notice this tendon, for example, is outside of the slab. So I'm just going to select the tendon and I'm going to move it inboard. I'm going to move it this way. So I can go back to modify, select modify after you've selected a tendon by coordinates, and we're going to move this over 0.2 feet. We'll just say move, and that's slightly within the slab. Let's move it a little bit more. Select the tendon again. Okay, and we'll do another, let's say 0.25. This is in the positive X, we'll say move. Okay, the other thing we want to do, by the way, if we turn off these strips, let's go back to floor design. I want to turn off the strips. Okay, the next thing we want to do is we want to try and combine these two, because we have a situation here where this line could really just be represented by one strand. This could be represented by one. Technically, we may not need both, like 4 tendons modeled. So if you wanted to modify that, we could take this tendon, delete it, this tendon, delete it, and then we have to increase the number of strands. So first thing we'll do is just take this, and I'm going to trim and extend this tendon up to the slab edge. If I go back to the tendon option, I can trim and extend it once it's selected. If we double click on this tendon, we're going to double this. We deleted one group of 5, so we need to double what's assigned to this group, and we'll do the same for this one. This will be 12. Okay, and we'll come back to those tendons to reassign their to reassign some of the properties. In this case, we're going to delete, let's say, this tendon. And this tendon is 4 strands. This tendon here is 6 strands. So we're going to change this one actually to 6. Excuse me, we'll change that to 12 because this was 6 times 2. So we're going to change this one to 12. We might have a little more pre-compression up in this area than we want. But again, here we're actually going to delete this out. We're going to run just one cable on this perimeter in this case. And the reason for this is we want to swerve one of these cables around. So the banding may not have been the most, I guess, prudent thing to do in this case, but we're just manually modifying now the cable. So this we're going to move this point out slightly, and I want to add a point to the cable. So let's save the model. If you select the cable and you right-click, say Insert Vertex, you could also go to Modify and insert a point. I'm going to insert a point there, and this basically inserts a span for the cable, and we'll move that like so. So this kind of moves out. We don't want it to move too far. away from that column, because that has to pick up the hyperstatic or the secondary reaction from the tendon. But we'll say that this is okay. We'll model it this way. And now what we want to do is modify control points if needed. So how do I view the tendon properties? Well, I could double click on any tendon, go into the shape system friction, and you can see like at this end, this has a tiny little span that's a reverse parabola, which doesn't make a lot of sense. That's because the program mapped the tendons to this location, and it maps it per the support line spans. So we need to get rid of that, or we need to modify it somehow. Secondly, if we go back to general, you can see all of the tendons here are modeled as straight lines. There's no spline modeling in this case. If we actually change this one to a spline, then the program allows us to swerve with more of a parabolic shape in plane around this corner. So we'll leave that one to spline. Once you do leave that to spline, then the program adds additional properties to the tendon. You can see there's this little double arrow. That means you technically could swerve that tendon out and it maintains fixity to the slab. So there's different things you can do with a spline tendon versus a linearized tendon. If we come back to this tendon and change it back to spline, you can see you can set the anchor settings for the tendon to the slab edge. We want this to be fixed at 90 degrees, for example, at the first and last end. And then we have just other properties. These are all set to effective force. All of the tendons will be. They're all set to 26.7 kips. So make sure your model has the same. We're now going to go ahead and modify the ends of tendons. Now in this, I want these two to be the same, so I'm actually going to right click and just delete out this point. And when I do that, you'll notice when we double click on this tendon, this actually has a long span. It comes in just the CG of the slab on this end. That's what we want there. So we don't really need to modify this end. Here we have a short span. We have that on the opposite end also. But this is really a true cantilever in this sense. We have a 4-foot cantilever right here. You'll notice it's modeled as a reverse parabola. Okay, so we need to change some things. We're going to go to tendon, and we're going to use the tendon editor. Select tendon editor, and in the tendon editor, you're going to go to shape. This gives me the end span shape, and it will actually show it on screen. This is a reverse parabola. So we're going to go and change this to cantilever down. And I'll just go ahead and select those yellow boxes. Those are editable points. This one will be cantilever down also. These are true reverse parabolas because we're going from this point all the way over to here. That's a real reverse parabola. There's no cantilever there. Change those to cantilever down. This one to cantilever down. And this, again, is the intent here is to fix kind of how things were modeled from the get-go. So we'll go back and change these also to cantilever down. And if I pause this, if I go now and look at that change, if I double click, you can see I have the right shape, but this is too high. I want this to basically exit out straight. So not only am I going to change the shape, we're going to also change the CG of the tendon. If I go to CGS, I'll resume this. You can see the NCG, this is from the top down. The NCG is 3.5 and the point interior is at 1. So you get that kind of steep cantilever down shape. We'll change this also to 3.5. And again, if I just click those points, that will modify the shape. Now these we really want at 1 foot or maybe 2 inches. So I'm going to change this to 2. I'll show you that here in a minute, and you guys can look at that for yourself. This I'm also going to change to 2. We'll come back to 3.5. Excuse me, this should be 4.25. This is a thicker slab, so we'll need to make that modification. That's 4.25 for these three. This one's okay. There's only one point there. Over on the upper side, again, we'll change this back to 3.5. We're now back at the 7-inch slab. Something like that. Now, this tendon, we actually may want to run this tendon here out to this point. Maybe we want to have some force out there on that cantilever. I'll move this one over. In that case, I'll come back and change this to 2 on this one. Okay, we're going to close that. Now, if you look now at the shape, I'll double click again on this first tendon. You see now this is straight. We changed the interior point to 3.5, so this exits out straight. Here we have a little bit of a reverse, or excuse me, a cantilever down shape for this 4-foot cantilever. Same thing here. We modified this one to a cantilever shape. Let me make sure that this is proper. This looks a little bit strange. So if we come back, let's go and change this to 0, just so we're kind of reset the datum. So this should actually be 2, and this should be 3.5, like that. Okay. If you turn on the 3D view, we could always go back to the visibility, or excuse me, to the home menu and scale this. So I could scale this vertically, and this would show the shapes a little bit better. Okay, so there's a couple of areas that are a little bit strange. You can see at this wall, this is a reverse parabola. That should really be straight. We don't need any profile there. The same thing right here. This should be straight along that wall. So we want to change those cables. We're going to say at the endpoint out here, we're going to run this as a straight shape. And we'll say it's 4.25. You may need to actually raise that up if you need more uplift in this span, but we'll leave it as this shape for now. And then the same thing for span 4 and span 6. These are at walls. We're going to change those to straight, and then we'll check that box to modify those, and we're done with the banded cables. Go back and reset the scale factor to the default and come back to the top view on the bottom user panel. Okay, for the modeling of tendons in the distributed direction, we're going to use, again, the tendon ribbon, but we're going to add what we call primary tendons, and we're going to copy those. And we're going to first determine what distribution we want for the distributed tendons. Remember, this is just a model. We're just representing them analytically. It may not exactly match what you want on plans. It could if you wanted to model things how you want them to be carried over into a drawing environment or in Revit, for example. But we'll say that we want the tendons spaced every 3 feet in this case. And so if we take our slab, and I'm actually going to be a little bit conservative, if we take the maximum thickness of this slab, you could also do this by region, but we'll say we have 8.5 inches times 36 inches, that's 306 square inches, and if we multiply that by the target pre-compression, I'll use 150 again, we get a force of 45.9 kips is required every 3 feet. So we're going to create a tendon, and if we take that force, we're going to divide it by our assumed effective force, which is 26.7. I need essentially 1.72 tendons per 3 feet. I'm just going to round it to 2. So I'm going to create 2 tendons every 3 feet. You technically can add 1.71 tendons as a decimal. For the demos, for this particular demo, we're just going to round it off to 2 and use that. So we're going to add a tendon. I'm going to model these left to right. And I'm going to start up here. At this point, we're going to click on the endpoint location of the tendon. I want to model these with orthogonal mode on. This is point 2, so we'll straddle, let's say, this split banded line, and then we'll come in here and we'll model this to the to the center or the perpendicular to this slab. There's the first tendon, okay? And this tendon doesn't represent all of the tendons that can be replicated downward because we have more spans to add, but this tendon will be 2 strands. The stressing is effective for is 26.7. The shape, we're going to want a reverse parabola in both spans, and we're maxing out the drape for the 2 spans. So 3.5 cg at the anchor on the left and the right, 1 inch from the bottom at midspan and 1 inch from the top at center. And I'm going to just copy this down. I'll copy it down once. We'll go to modify, and this will be in the negative y direction. We'll copy it like so. And now I'm going to use this tendon to create a new primary, keeping the 3-foot spacing. I'll just drag this tendon out to there, and then I'm going to add a point. We'll add a point 1. I'll add, let's see, we need to add basically 3 points. Okay, once we do that, I've escaped. I'm going to move the point. So I'll move this so it intersects this band, this band. These will be straight. You might get a little bit of drape as you move towards the wall, but we're going to keep them straight. And then this is going to be just straddling kind of the center of this band. It's split, but we'll say it'll just come over the top of this banded line. And then we anchor it out here at the perimeter. Again, you could make a case this is a cantilever, so we need another point, but we'll just assume that we're running it to the edge of the slab. So we have an extra point actually. So let's save the model, select this, and we'll right-click, delete this vertex here, and we're left with this tendon. Now, if you double-click on this tendon, we still have this set to 2, that's what we want, but now we have a modification for span 2. This is going to be straight. Remember, there's actually a band here and here that stretches and splays, so we want to make sure that that's the proper assignment. And we're going to copy that down multiple times. So the span is around 30 feet. These are 3-foot spacings. I'm going to copy this in the negative 3-foot direction, y direction 9 times. And what I need to do is just select those. I'm turning on only snap to intersection, turn off snap to nearest, and we can just move these over in place where we want them. Now again, if we needed to add some drape to control the uplift, we could do that by coming back into the property of each individual tendon and creating a reverse parabolic shape. But as we get closer and closer to the wall, we get less deformation. We're getting help from this banded line. So we're going to leave this as a straight shape in this wedge. I'll go ahead and draw that wedge. This is all straight in terms of the profile here for the demo. We'll do the same thing here. This will be straight over the wall. And along this path, again, these all anchor at the edge. You could again make a case this is a cantilever. However, there's a column here. It's not a true cantilever in that sense. So that's the replication of the tendon over that let's say first bay. We're going to do the same thing now for the second bay. What I'm going to do is actually copy this tendon. This one's aligned perfectly orthogonal. This one I moved up to the midpoint of the wall, so there's a little bit of skew to that one. Select this tendon and copy it down negative 6 feet. Okay, we have this tendon now, and I'm going to copy it again, negative 6 feet. Oh, excuse me, let me go back and copy that. Let's see, 3 feet. It should have been 3 feet. We'll copy that again. Just delete this one. And let's get this aligned. Now, in this case, we are going to come back and we're going to add a profile to this span here. This, we're going to make sure that that's centered. So once you select that point, turn on snap to nearest, and you can click on a point along the tendon. Just center that by just eyeballing that. And then for here, we want to trim that back to the slab edge. If I go back to tendon, trim and extend, you'll notice if we go to the tendon settings, we're going to increase this to 6 feet. Now if I select these two tendons and I trim and extend them, they'll trim back to the proper location. Okay, this tendon we're going to copy down a few times. We'll copy that down 7 times. But before I do that, I'll go to the properties and make sure this gets changed to reverse parabola. So change that to reverse parabola. It's a short span. We're going to go back and create a CG of, let's say, 4 inches. We don't need much uplift. Here it's about half a kip per foot of uplift. We can modify it as needed later once we look at the results, but we're going to now copy this one down using modify by coordinates. Again, -3 feet. We'll copy this down 7 times. This tendon I want to split, so I'm going to select the tendon. Let's save the model. Select that tendon that goes through the opening, right click, and delete out the vertex. 2 of them. Again, if you select this and you choose to trim and extend under the tendon tool, it will trim to the face of the opening. What I'll do now is I'll take this tendon again. I'm going to use it as just a guide, and I'll copy it down again, -6. If I select it, I can do the same thing. I can trim or delete vertices from the right to the left, and then trim and extend. And we have that split tendon now on that opening location. We'll do the same thing here, but we'll do that here in a moment. We're going to go back to modify by coordinates. We're going to copy down 3 feet, and we'll change it. We'll say 4 copies. We'll delete one of them. Okay, we have a tendon here that's along a wall. So for that tendon, I want to change that shape back to a straight shape for span 2. You can see there's a little of a jog there, so you might actually want to drop this down to 2 inches, so it's aligned straight. Here we get back into the slab, so we want some uplift there. We'll leave that one as is. We do need to add a point potentially here if we wanted to add a secondary point here. This is a longer, or I guess it's equal to this, so we'll leave that as is. It's similar on the top, so we'll leave it as we did it on the top. And again, for this one, we'll right click, delete the vertices, and we'll take this and use trim extend again to push that out, and then we can copy this one down several times. So we'll copy that down 9 times. This will be a -3 foot distance, and copy. And I might want to move that inboard, so we'll take that and just move it. Select that tendon that falls outside of the slab and move it up, say by 1 foot, just say move. Okay, the same thing applies for this tendon. I'm going to delete point 1 and 2, and then trim and extend this tendon. I'll take this tendon again. I'll copy this down. Instead of 6 like the one above, we'll do 3 because this is aligned orthogonally, so this is going to be -3. Take that copy, right click, and delete out the vertices. Oops, wrong one. Let me undo that. It should be this one. So right click after you've selected, and then trim and extend the tendon. We now have a model with everything built. We're now going to run through the process of analyzing and designing the system. If you wanted to view the model, you can go to Visibility, Render Model. This gives you a nice view of the modeled structure with tendons. And this helps you also confirm some of the modeling in case there are any issues with the tendon modeling. Okay, so we don't want to see the tendons, let's say in this case. We're going to turn the tendons off. We can go to tendon, turn those off in display. We'll go now to analysis. First thing we need to do is mesh the structure. So we'll mesh this using simplified settings, and we'll use the default settings, and the program will mesh this slab. Once we mesh the slab, we're going to analyze the slab. So we don't really need any of this. This is all applicable only really to multi-story modeling. We're just going to use the default properties. We're using an uncracked usage case. That means we have not assigned any modifiers to any of the components for simulating cracking. And we'll just go ahead now and execute the model. You'll notice that there's a few errors. So we have some issues with cells straddling over walls, and that probably is caused by some of our slab modeling on this edge. So we may need to clean that up. We'll go ahead and do that now. What I'll do here is I'm actually going to move this slab and I'll align it with the wall. I think that's going to help us in this case. So let's do that. Use the align tool and orthogonal again, like we had done at the beginning of the demo. And we're going to take this slab and just move it over. I'll move this one over to here, and then I'll move this slab over like so. And see if this meshes properly. Do not want to delete the opening. Once you've done that, save it. I'm going to turn my tendons back on, and if I just select by type under the home menu, select all tendons, and then use the option to trim and extend, it will trim all of our tendons back, and we should be okay with that. So we'll now turn the tendons off. Let's go back and remesh. So we'll just run the meshing again. Okay, we still have some issues here with the meshing. You can see it's encroaching in the opening. So let's go ahead and for this example, let's remove that. What we would have to do is actually realign some of the slabs. We might have to take this slab and actually cut it up to here and then add a new slab region. In fact, let's give that a go before we remove the opening. So if we take this slab, I'm going to actually move it to this point and this point, and I'm going to actually delete the opening. We're going to create the opening out of the way we model the slabs, and then I'll model just another slab. Turn off snap orthogonal. We'll model another slab that looks like that. Okay, this slab, we're going to double click on it, make sure it's 7 inches with a 0-inch offset. Okay, so that should fix that issue. Let's mesh again. We should get a clean mesh now around that opening. This one also looks to be problematic. Let's see what's going on here. Make sure these are referenced at the right. It's at level 2. Let's just remodel this one. We'll delete it, come back, just reassign it. Okay, and that worked there. So this should run for us. We'll come back and execute the analysis for the model. Okay, so once we analyze, we get some results here. For example, for surface total, this is the uncracked condition. We could turn on, the slab deflection. We get max deflection of about 1.2 inches here. So looking at a deformed shape, I could turn on this contour, come back to my visibility render model tool, and this allows us to look at that deformation in the slab. So You could also look at this view as well if you click on this Z deformation button. Clearly that's the location where we are likely going to have some stress issues. So let's go back. I'll turn off my shell elements. I can either use my default display, which is set under view settings. You select the components, save as default, and that will allow us to save a default display to always come back to, if you will. We're now going to generate the floor design, and we're going to generate our sections again, and we're going to design the sections. So there's this option here to design the design sections. And this basically processes the design. It calculates stresses, balance loading, pre-compression, etc. for the PT design. So the first thing we'll look at once that's done is our pre-compression. I want to isolate the direction. So if we come back to the visibility for the design strips, we'll isolate the X direction. I want to check this for service total condition. Under the option for design sections, we're going to go to stresses, and we can see for pre-compression there's two options. We'll use number of tendons, and if you wanted to see a value, this is showing max min, we could turn on the numerical display option here under strip results visibility. This gives us a value for each design cut. You can control the decimal location. Maybe we just want one significant digit, and we might want to reduce the font height, let's say to 4, and then I'll update that. But our pre-compression is right around 200 for most of these strips, maybe a little more, and we're okay in the X direction for pre-compression. If I toggle now, I'll turn off X and turn on Y, we also are okay with pre-compression. The number of tendons option here under analysis is based on summing the total force intersecting each design cut. Has nothing to do with the in-plane stiffness of the slab and the potential for slab restraint. If you use pre-compression, this first option, this considers any in-plane restraint. So you can see these are not perfectly, we'll switch back to the X, these are not perfectly flat graphs. Here you might have some loss of pre-compression in the slab due to in-plane restraint or due to opposing forces in tendons in the opposite direction. There's any number of reasons why you might get a drop in the diagram like this. So in this case, we meet both conditions for both directions. The next thing I'll do is look at the bottom stresses for service total, and you would want to do this for sustained and also for initial. You can see clearly that in these longer bays, on these outer bays, we have overstress on each one of these strips in the total service condition, where the max is really location 1 and 2. So here we violate 6 times square root of F prime C, and the stress for these strips is right around, hovering around 720 psi. This is 650 psi. So we need to do something to fix these problem areas. If we turn on the tendons again, what will likely be required is for us to actually add tendons in this, add force in this outer bay. So right now the force might be, for example, 20 kips per foot, or 20, 26, 27, 28, whatever kips per foot from here to here based on the distribution of this tendon. We might have to bump that up to 40 kips per foot. So that might mean we have to add tendons in between each existing tendon to get these stresses to be worked out. The top stress, let's turn off the tendons again. If we toggle now to top stress, we have a couple of locations where top stress is exceeding allowable. Those would be worked out once we solve bottom stress most likely. And then we also will need to check the Y direction. In the Y direction we also have issues. So we have banded tendons here. We might have to add tendons to the bands in these two locations. We have a banded tendon running already continuous. We might have to add more cables there. In the other direction, again, we might have to add a tendon, or we might just increase the number of tendons for the existing two tendons in this strip, and then we have a couple of issues over here. The last thing to check would be the balance loading. If we look at the load balancing, I'll just use a simplified. The target is actually set under display. The balance loading maximum is set to 100%. So graphically we check against the maximum, and we're clearly overbalancing the slab. 108% here, 154 here. So if we look at the tendons again, and we come in and look at the CG of these cables, if I go to the tendon editor, the CG for this cable, let me turn off the load balancing for a minute, is 1 inch. You can see that's 1 right there. That's from the bottom up. And then the same thing down here, 1. We might have to raise those tendons vertically. By doing that, we lose some of the counteractive nature of the post-tensioning, so our stresses will increase. So before I move the cables, before the user moves the cables, we were going to come back and just look at the stresses. The stress here at the bottom is in compression. That's a good sign if we're wanting to move the cable. Here it's in tension. The allowable tensile stress is, you can see right here is 424. That's 6 times square root of 5,000. Here we're at 280. So we could stand to raise this up a little bit from 1 maybe to 2 to 3 and still be within allowable, but our stress is increasing, and here clearly we can move it up to meet the balance loading. So that's another check you may want to make in design of the slab, is how much load are we balancing. And if I go back to floor design and look at the load balancing again, we have some other areas where it's over, where we may need to adjust the cable, as long as we don't sacrifice the stress. If you lift the cable up and your stresses exceed allowable, then you're violating the code requirement for allowable. So those are just different things we have to ensure that we fix, or that we go ahead and we satisfy the code requirements for those conditions before we move on to a strength check. This particular demo is not necessarily intended to show that operation. What I would do is, if you go back to youtube.com/adaptsupport and you check out the tendon optimizer videos, that's going to show you how to use the optimizer to more rapidly produce results for overstressed areas like that. The next thing we're going to do is we're going to assume that the stresses, the precompression, the balance loading all work out for this model, and we're going to go ahead and calculate the reinforcement. And we can calculate it for the envelope or for different combinations and so on. We'll calculate the rebar, and this is now the reinforcement produced for this particular model. If you wanted to display it differently, we can always go to the rebar option, display manager. We can show calculated, that's what the program has produced, versus user defined, which we call base rebar. We have not added any base rebar to this model, but we can isolate it in the X or Y, top or bottom directions to produce different views of the reinforcement. And the blue rebar just indicates that the piece of rebar is actually extending through different slab thicknesses. So this goes from one slab that's offset to one slab that's not. It's at the top of the slab, so it's mainly just a detail warning. This bar, if you're not careful, may stick out of the slab if you don't detail it properly, and that's what the blue reinforcement typically will indicate. This one here is also a similar warning. This is probably there because the distribution of 55 bars would go into one slab that's offset and one slab that is not. So this is how we would produce reinforcement for a given project, and then from this we can export rebar to different environments. We could export it to Revit or to a DWG file using this option. If we wanted to export it to Revit, we would export this DWG file or an IMP file. This IMP file would be used to then read into Revit and produce objects for reinforcement. The last thing to show in this demo really would be a couple of things. One is the demand capacity curves. If we turn off the rebar, I'll turn off this. Under investigate, let's collapse this, and I'll come back to design sections, investigation, moment capacity with demand. This is going to show us, let's go back to the floor design and turn on the section cuts. This will show us the blue is the negative capacity, green is positive capacity, gray is the demand. So this is at strength level. Here you can see this one actually shows a pink section. That means that the convergence on the section is something just slightly over 1. You can see this is 1.002. But this, if you double click on any design cut, you can obtain section information for properties of sections, reinforcement, and a design summary for that particular section. We had set up a couple of crack deflection combos, so we're going to run that now as the last part of this demo. And we're going to go to analysis. After you've analyzed and designed the strips, we can run the crack deflection check and produce the total cracked deflection with consideration of creep. Once we've done that, I'll come back to my default display from visibility. We're going to go back to loads. Under loads, we're going to change this to long-term deflection, and we'll do cracked long-term deflection, and under the slab deformation value, select the Z value, and you can see this is 3.1 inches of deflection in this zone. So that may not even meet the requirements for this design, but that's what's being produced for this. Clearly we need more post-tensioning here, not only for stresses, but also that would assist in controlling the deflection. If you wanted to check the loss of stiffness for the slab, we would then have to select a cracked deflection case. Let's say cracked, you can see this is added, cracked underscore total CR. We define total CR. My objective now is to take that one crack deflection case, and if we look at the actions for the slab under that one case, we can turn on the reduced rotational stiffness about the X and Y directions, and you can see this, we're losing about 50% stiffness due to cracking in this zone where we have that maximum span. It's an outer bay, and we're losing some stiffness here, also bending about the Y direction as well. If you have any questions about the demo or wanted to request this model, please contact us at support@adaptsoft.com. Thank you.